Hey guys, today we're talking about kinetics. We just wrapped it up, but want to make sure we do have a quick refresher. So kinetics is focusing on how fast something's going. So reaction, stoichiometry, how much do we start with, how much do we end with, spontaneity, thermodynamics, will it happen, won't it happen, equilibrium, how far does it go, how much do we start with, how much do we end with. Kinetics is just how fast does this turn into that. So make sure when you're talking about kinetics, lowercase k's in terms of rate law constants, anything like that, that you're focusing on just does it go fast or slow? That doesn't have anything to do with the equilibrium constant, doesn't have anything necessarily to do with the thermodynamics. So very likely we could get into things that cause a reaction to go faster or slower. Sometimes it's just what we have in terms of our reactants. It could be whether they're strong or weak acids and how ionized they are. It could be how strong or weak the bonds are. The stronger the bond, the more energy it takes when we are breaking it. But we'd have to have more information there. We'd have to be comparing some things there. But the things that are just straight up normal reaction rates are concentrations. More molecules, more collisions, faster reaction. Surface area, more spread out, more exposed, more collisions, faster reaction. Higher temperature, faster moving particles. This is the key one. It can also come up in gases, but definitely here in kinetics, our collisions are more frequent. Our collisions are more energetic. Both of those are important, and those are two different things. So remember that. What happens here when we have a higher temperature, it's that more of our particles have more kinetic energy, therefore more of them get over that energy threshold, or a key term, the activation energy. Catalysts also speed things up. We'll refer to those at the end. Catalysts do not make it hotter, and heat is not a catalyst. Those are different things. So make sure you're aware of that. So they speed up the reaction. They do that by changing the pathway. They do that by lowering the activation energy. And all of those things come into the collision theory. They have to collide. They have to collide with enough energy. They have to collide with the proper orientation. Those are some important differences. Energy and orientation are different things if they ask for two justifications or explanations. When we are talking about kinetics, it's all about reaction rate, how fast it's going, or it could be any measurable change that we have over time. So a lot of times it's change in concentration. It could be change in pH. It could be change in absorbance. It could be change in pressure. But any measurable quantity that is changing over time. A lot of times we look at the average rate. An important one right here that connects with stoichiometry is relative rate. How fast is one being consumed compared to another? If it's got a coefficient of 2, not only do we need twice as much of it, but it gets used twice as fast. But a lot of times we're looking at the instantaneous rate at this moment, at the beginning, after this long, how fast is it going? And sometimes we'll look at average rate, but a lot of times with graphs, we're getting into instantaneous rate. So probably in terms of rate, the relative rate is maybe the most important thing that we forget, is just that we can compare. If I know how fast one thing's going away or being made, the coefficients and the stoichiometry explain how fast the other thing's happening. We use that data to make something a rate law. It is an equation that shows how the overall rate over here compares to or is influenced by the concentration of each of the reactants. Once again, our exponents are the order. They aren't necessarily, and in most cases, are not the exponents. So this is not something we can get just by looking at the reaction. Rate laws, reaction rate, relative rate, integrated, differential rate law, all of that is based upon lab data. K is a rate constant, but it can change. If we make it hotter, it goes faster, new K. Different reactants, faster, new K. But if it's speeding up just because we're changing our concentrations, that is what's making our rate faster without changing our K. So orders are either first, second, third. It technically can be zero order. It could be higher order than that, but it's where we come up with these different equations. Well, first order is something to the first power. Second order is something to the second, or two things to the first. We can predict and know what the unit would be on K based upon the overall order. It's something that you could write down, you could put on a cheat sheet and just have there in front of you, instead of having to worry about figuring it out. But what's important here is that concentration is always going to be moles per liter. That's how it's going to be presented to us. Our rate is always going to be presented as molarity per time, or moles per liter times time. So K is whatever is necessary so that cancels out. On the normal AP exam, I would say do not try to memorize these things. Just worry about canceling the left and the right side. But this is something you could put on a cheat sheet, since you've got that in front of you, where you don't even have to worry about canceling. You just know what it is. Also, make sure that makes sense to you, that you know what that means, in case you're asking, well, why are these the units? K is just somewhat of an arbitrary number that makes the connection between our measured experimental concentration and our measured experimental speed. And the unit on it is just so that those two things can relate to one another. The first way that we can take lab data and figure out the rate law is the differential rate law. You don't need to know them by names, but that's when we're looking at, okay, I doubled the concentration, nothing happened to the rate here. When I change this concentration, something does happen to the rate. So when you're doing that, you keep all of the other variables constant, change just one concentration, and see what happens to the rate. If you are asked to explain this, be super specific. When A is doubled while B stays constant, this stays the same. Therefore, it is zero order. When A stays constant and B changes in this way, this happens to the order or the reaction. Therefore, it's zero, first, second, third, whatever order it is. Be very specific. It's a lot easier to put it into words, maybe, than do it with math. But there are ways to support it with math as well that we have done. The integrated rate laws, even a little bit easier. This is when we're graphing things related to concentration and time. It technically could be even pH versus time, or most likely absorbance versus time, since absorbance and concentration are directly related to one another. But we have a graph. When it is just concentration versus time is a straight line, that's zero order. It doesn't matter how fast, how much we have, it goes at that same speed. Burning the candle was that. If it's natural log versus time is a straight line, that's first order. That's what happened with crystal violet. If it's the reciprocal, or 1 over the concentration or absorbance versus time, it's the straight line. Each one produces a different graph here, but they're all variations on y equals mx plus b. The m is the k, or better than that, the absolute value of the slope is the k, because k has to be a positive value. There is a positive relationship between your concentration and how fast it's going. It doesn't make sense for that to be a negative, because that would mean the more concentration I have, not just that it goes slower, but that the opposite is occurring. So we're always graphing in this way. One thing that's important with this is that first order, we didn't really mention it up before. That is the only type of reaction that has a constant half-life. So it's talking about the half-life is a certain amount of time. That's because it's a first order reaction. So in that case, our concentration versus time would be a curve. Natural log would end up straight. And we can use the equation, which is given, that the half-life is 0.693 over k. And that all comes down to the natural log of 1/2. That's where all those numbers come from. But we can make, even if I don't have a graph, maybe even if I don't have a whole bunch of stuff with rate and with all of those other things, I can still make a connection knowing that k is related to half-life and half-life is related to k for first order only. So if they're asking about it, it would either be a first order, or you would say, well, the half-life is changing. I can't do it, or I can't explain it that way. But we did several with these, and this is really, hopefully, easy and straightforward. Mechanisms are a really likely thing to maybe have to explain. The idea of the mechanism is, instead of just looking at our overall balanced equation, we're breaking it down into the individual steps. Catalysts are involved, intermediates are involved. You can read these things. I'm not just going to read paragraphs to you here. I already talked too much. The idea is the mechanism breaks that overall thing down into a couple steps. There's a good video, one that I did watch by the College Board, where they do talk about the mechanisms. If you're still stuck, if my videos didn't make sense, check out the College Board videos on that. Those are posted on their website under those COVID resources. If you still don't totally get mechanisms and what I say doesn't clear it up, but there's a couple ways of approaching it. One is you just write all of your reactions, then you look for where is the slow step. You draw a line under the slow step, you cross off any intermediates because we didn't put the intermediates in, so they can't be a part of our overall rate law. But then you just see above that line that you drew, how many times does each chemical appear on the reactants side? If it appears on the reactant side one time, it's first order. Two times, it's second order. So the example we used on our kinetics test, a lot of people got kind of stuck on because they were looking at just the slow step as the rate determining step, which it looks like I have spelled wrong right down here, determining. It's not just the slow step. The slow is rate determining, but it's everything up to and including that. So if you start with a couple fast steps, those would be in your rate law as well. And as we're doing that, we are making sure two things are true. First of all, does the reaction cancel out to give us the right reaction? This is kind of like we were talking about earlier. The temperature makes it collide with more energy and more often. That's two answers. Two ways we can prove a mechanism is, does it add up to the right overall reaction? That is proving or connecting the stoichiometry. It has to do that. But then it also has to connect to the rate law. It has to have the right number of appearances of each thing up to and including the rate determining step or the slow step. So if N2 is second order, there have to be two N2s before that line that we drew after the slow step. So that's why I underlined it up to and including here. So with mechanisms, we could either be given the rate law and given a mechanism to see if it supports. We could be asked which step is the slow step. Well, we would just keep going until we get enough steps till the number of each thing matches up with our rate law. Potential energy diagrams are a great connection between thermo and kinetics. You're not going to have to draw them, but being asked about them or thinking about them. So right here, this uphill, we think about that as the energy to break all of the bonds in our reactants, or in terms of kinetics, that B right there, that is the activation energy, and it's got it listed right there. So in order to break all the bonds, get the reaction started, that's the activation energy. A really high hill means a very slow reaction because a lot of energy is needed. That goes back to the nature of the reactants there. C is the energy released when the bonds are formed to make products. D right there is the difference between reactants and products, or the delta H. In this case, it's negative, so it's an exothermic. A and E aren't really as much, but they're kind of looking at the potential energy relative to either zero or some arbitrary value. We don't care about that as much. But when we have a multi-step mechanism, there's going to be more than one hill. Each hill is another reaction that's happening because it's more bonds to break, and more bonds that are made. Up here, it says the rate determining step is the highest activation energy. Well, that's the most energy to do it, so that's why that one's the slowest. It's the most energy that needs to be put in. So it is possible to have a small first step and a big second step. We can also, and we know this with equilibrium, we can look backwards. So a lot of this labels things as forwards. We can go backwards on it, and that's a really good connection between activation energy, thermo, equilibrium, kinetics, where they're going to talk about the forward and the reverse. Well, reverse just means start over here, go backwards. Well, now the activation energy is C. On this one, the bonds of the reactants in the backwards would be C. The bonds of the products would be B. The D, the delta H is the same, but now it's positive. And catalysts, once again, we said that they speed up the reaction. They do not make it hotter. they lower the activation energy in some way. So this is a good one. A lot of times, and especially in Chem 1, we draw a big hill and then a smaller hill. Well, they have to be giving a new path, which means a new mechanism. So we've got a big hill. We've got two hills here. They are smaller. It is catalyzed. Just because it's showing one hill doesn't necessarily mean that it's a one-step reaction. They're just kind of simplifying it. But if they are showing two hills or three hills in your mechanism, that does mean a 2 or 3 step reaction. So one could be one step, or it could just be the overall simplified potential energy diagram. But when they're showing those multiple steps, that's important. So once again, it doesn't heat it up. It doesn't make it move faster. It allows those molecules that are still slow to react. They don't need this much energy. They only need this much. Or over here, we have the same number of particles that have that much energy, but now this next chunk can react because maybe the way that they're lining up, maybe the bonds that need to be broken or made are different, so it's requiring a different amount of energy. So that was the overall version of kinetics, the shorter, the overview version. Remember, this and any topic that my overview isn't good on, we've got the videos from way back when, but maybe more importantly would be hearing it in a different way. The College Board has all of those videos right now. Go check those out. Those are your Friday's optional work, but spread them out throughout the time. Focus on the ones that you feel like you need. If the overview makes you feel like you're clicking on all cylinders, then be done. Do the overview, make a review sheet, look at a few problems and move on. If the overview makes you feel kind of self-conscious because you don't know what you want to know or don't know as much as you feel like you should know, then either go to an old video, old notes, go to the old worksheets that you did, or really that's the thing to focus on the College Board videos. So there we go. Optional Monday e-learning for kinetics. Thanks a bunch.